This week in lab, we'll be looking at the kinetics of a reaction of a dye called Crystal Violet. And this is a purple dye, which is why we have the name, but it will react with hydroxide and form a colorless molecule, as shown in this reaction here. But initially, when the dye is unreacted, we can measure the amount of dye in solution based on the absorbance of light within the visible region at lambda max, and that will determine what that lambda max is, but we see a purple color, and over time it becomes a colorless solution, and so the absorbance will be decreasing. If we wanted to kind of simplify this reaction rather than seeing these big organic structures, we could write it as Cv plus to represent the purple dye, and OH minus as our hydroxide ion, and then the product would be CvOH. If we wanted to consider what the rate of this reaction would be, the typical format for a rate law is that rate is equal to K, the rate constant, times the concentration of each reactant raised to their kinetic orders. We do not know going into this what the kinetic orders are, so that is something that we will be determining so that we know the overall rate law for this reaction. And so it's important to recall that rate depends on the concentrations of reactants as expressed in the rate law. So what the concentration of Cv plus initially is and what the concentration of hydroxide initially is will determine that rate. Also, the temperature of the reaction solution will matter for the rate, and that's because at higher temperatures you have a larger proportion of molecules that can overcome the activation energy barrier compared to at a lower temperature. And we'll look at both of these concepts in this experiment. So first, thinking about concentration and rate. If we were to think about what's going on in solution over time, we start out with some high concentration of the crystal violet in its purple form, the Cv+, and over time that will decrease. And so we'll actually be measuring the absorbance of this to determine what the shape of that rate decay would look like. But if we think about the concentration of the product, our colorless species, initially it would be 0, and as the reaction proceeds over time, we start to form some of that product until we kind of level out at the max amount of product we're going to produce. We could consider mathematically the rate as the change in concentration over the change in time. So if we took two different points, kind of whatever range we found to be important, we could measure an average rate over that time period. And so that is expressed in this delta concentration Cv plus over delta T. That is an average rate. This is the type of rate we were concerned with in our kinetics of the iodine clock reaction experiment. If we were, however, to be interested in what's the rate at this point of the reaction versus at this point, we could measure an instantaneous rate at each of these points by essentially measuring the slope of the tangent line. And so that is the same thing as determining the derivative at that point. And so dCv over dt is our instantaneous rate. All right, so that's conceptually what we're trying to do in this experiment is look at instantaneous rates, but we're going to kind of think about the instantaneous rate at all points combined in a sense, because we're going to be more focused on what the overall shape of the graph is and how we can consider it to be linear. And so to simplify our rate law so that we can actually make these approximations, we're going to actually prepare our solutions in a way where the hydroxide is at a really high concentration compared to our crystal violet. So I've drawn here a whole bunch of black dots to represent the hydroxide ions and just one purple dot to represent the crystal violet dye. And then after the reaction happens, one hydroxide and this purple crystal violet dye molecule have reacted to produce one CvOH molecule, represented by the pink. If we were to say there was a 1,000 to 1 ratio in the initial reaction flask, then after the reaction we have a 999 to 1 ratio. And so because the order of magnitude of hydroxide is so much higher than the order of magnitude of the crystal violet, we can essentially treat the hydroxide concentration as a constant value. And this means we're essentially eliminating the hydroxide term from our rate law in order to focus on what might be the order of the crystal violet. So that changes our rate constant slightly. It becomes a K observed rather than the actual rate constant, but it simplifies it enough that we are actually able to draw some conclusions. Now, we won't know exactly what the concentration of crystal violet is because we're not going to go through the process of creating a Beer's law plot and relating absorbance to concentration first. We're just going to treat absorbance as a proxy for concentration because they are directly proportional to one another. So we'll measure the absorbance of crystal violet, and let's recall that there are 3 possible kinetic orders for a crystal violet reactant. It could be a 0, a 1, or a 2. And so based on the shape of the curve that we obtain when we take measurements of the absorbance over time, we can determine what that kinetic order is. And this is done by considering the possible integrated rate laws. So each integrated rate law predicts what transformation would be necessary in order to linearize the data. And if likely you might want a refresher on this, if our reactant is 0th order reactant, then just the concentration versus time would be a linear relationship. If our reactant was 1st order, then the natural log of that concentration versus time would be a linear relationship. And then if it was 2nd order, 1 over the concentration versus time would be linear. So we're actually going to take our data and we're going to do each of these transformations to the concentration in order to see which gives the highest degree of linearity. After we've finished that, we will also compare the concentrations of hydroxide at multiple different levels so that we can try to intuit what the kinetic order of hydroxide is in addition to just this crystal violet. In the second part of the experiment, we'll also consider the effective temperature on the rate of the reaction. So let's recall that in order for a reaction to occur, the 2 reacting particles have to actually come into contact with one another. They have to collide, is another way to say that. And so the particles are moving with a specific speed, and that speed is related to the energy that the particle has at that moment, kinetic energy. So when the particles collide, as their first requirement for the reaction to occur, second requirement is, do they have sufficient energy that they can overcome that activation energy for the reaction that is necessary? So energy greater than whatever the activation energy of the reaction is. And the last criteria is that they would be in a correct orientation. And some molecules become more and more complex to where that orientation becomes really important. But we're not going to consider that factor here. We're really going to look at just the energy and activation energy consideration. And the relationship between the activation energy, temperature, and the rate is given by the Arrhenius equation, where we have the rate constant equal to the frequency factor A times E raised to the negative activation energy over RT. And this equation kind of shows us that as temperature increases, the rate constant also increases. And so that would mean that higher temperature would generally yield a faster reaction. So we can transform the equation into the natural log form so that it will become more useful for us for plotting purposes. So if you take the natural log initially of that formula, you get ln k is equal to ln a minus EA over RT using the properties of logs. But we can rearrange this even further to make it a bit more familiar for a linear relationship for plotting purposes. So natural log of k, if we are to pull out the EA over R term from the 1 over T, kind of separate them a little bit, we can see that temperature is something that's easily manipulatable, so it can be our independent variable, or x. So 1 over T can be our x, essentially. And then that leaves the rest of this, which are constant values, to be our m. And we will measure that by getting the slope of a line. And then we have also our b term, which is y-intercept. That would be the natural log of the frequency factor. So we can pull all of that information from a plot. And so to actually make the plot, whatever rate constants you have calculated for each of your different temperature data points, once you know the rate law, you can actually calculate the rate constant. If we take the natural log of those values for our y, and we take 1 over the temperature that we set it to as our x values, we can get a plot of our data and get a nice line fit, hopefully without too much error, good correlation. But that essentially will tell us what our activation energy is, because the slope of the line will be equal to negative EA over R, and we can solve for activation energy in that relationship.